Okay. Okay, so yeah, I hope the screen is visible.
Yes, ma'am.
Yes.
Yes.
All right. Okay, cool. So yeah, so what we were doing was these multi-agent search. Okay, and so we moved from the search, the single agent case to the case of when you have multiple agents, and here we said of this model where it looks quite similar to what you had before, but you have like more players. And all these things are the same: the transition function, the set of states, actions, the transition function, and there's also this terminal test, which tells you whether you've reached the end of the game or not. And there is this terminal utilities. So rather than a goal, you capture what is desirable by means of these terminal utilities, because here there are multiple players. So what is good for one may or may not be good for the other. So that's why you have this notion of utilities here rather than a goal state. In the case of search problems, you just had like one agent. So whatever was good for that one agent, that was called as a goal. Okay, so just to connect these two. And the typical framework works like this. There's a start state, there's one agent who acts, and you go into new state of the game. Then the next agent comes in, then the state changes, and so on. And after n states, if there are n agents after n actions, then again it goes back to agent one, and it continues. Like your typical game of any game that you play. For example, cards, you have these rounds, right? So this is something like that. It's actually exactly that. And we saw this notion of two-player games where the players are playing to hurt each other. So one player's win is equal to the other player's loss. So if Pac-Man wins, the ghost loses. And okay, so that's what we saw in two-player games. Now here I have to tell you that these kind of games or these kind of search problems that we are looking at, it's quite connected with a field called game theory. Okay, so the focus many times in game theory is something like you want the system to go into an equilibrium, so you want it to be in a stable state, and so somebody tells you what is the strategies. But the essential idea is this, that you have different players who have a set of actions, and they have some set of strategies which they have to decide. They have to choose one strategy to play. Okay, and you have these utilities concept there too. So, these were some examples that we had of terminal utilities. And then I told you about this adversarial game tree, where it looked very similar to the search tree that you saw in single agent case, but just that like at each level the control is with a different person. So in the first level, Pac-Man starts, the root node, Pac-Man starts, chooses some actions, and then the ghost comes in the next level. So now in this set of states, the ghost has the control and chooses which action to play. And in the next level, again, the control goes to Pac-Man, and so on. It alternates. So these were actually, what we saw was just a set of two-player games. Okay, so it went on like this until finally the game ends. And in the last, you write the utilities for Pac-Man. Okay, because Pac-Man is the agent that you represent, or whatever, the max. It's also called the max agent because you're trying to mimic an agent which tries to maximize the utilities, and Ghost is the min agent. Okay, so you have a max agent and a min agent, and the terminal utilities are all written for the max agent. So in that case, what the min agent will try to do is it will try to play an action which is trying to hurt Pac-Man. It's trying to minimize these numbers, because the utilities are such that they're equal and opposite. So in the terminal states, if Pac-Man has 100, for Ghost it's minus 100, right? So what Pac-Man should try to maximize and Ghost will try to minimize. So that's sort of the framework of these games. And so you're trying to, and these kind of agents that you are trying to mimic those are called min-max agents. And the goal is to now find a strategy. What is the strategy that the players should play? Okay, and we saw one example here. So let me just get back to that example. I'll just remove these parts because this was, I guess, for a question that was asked that I wrote it. Okay, so just to be clear. Okay. Yeah, so we saw that, this was just very quickly over this example. We had these these utilities, and the first player was a max agent and the second player was a min agent, and then the game ended. So at S2, at state S2, it was being controlled by a min agent. So the min agent would always choose the lowest, okay, of these three numbers. So he could choose B1. And so the value of the state is the best achievable utility at that state. Okay, so here the best achievable utility was -8. And similarly for S3, it was -3. Okay. And now it came back to P1. You go back up the tree. And now when P1 sees, the first agent sees these two states, the values are -8 and -3, and it's going to choose whatever is highest. So it's the best action here is action A2. Okay, so that's for the max player. So I hope this example was clear. Right? Were there any questions on this example? Okay. Was it clear? Can you just type?
Yes, ma'am.
Clear, ma'am.
Yes, ma'am.
Clear? Right. Okay. So, so what actually this is capturing is that you assume that the worst is for you. Like you assume that the other player is going to play something that hurts you the most. And then you, it's like a very risk-averse strategy. It's a very careful strategy. And so even if the player plays the worst possible for you, still you try to do as best as possible. Okay. So let's just write the formal algorithm quickly. So what you would do is, you have a function here which is trying to give you the value of some state. So that is the main function. So you call this at the root node. And okay, so at some point, if the state is a terminal state already, if state is terminal, then you just, what you return is just the utility, right? So if you come to this state, what you're just going to return is -8. Okay, so you just return the, utility of that state. Utility of that state. Okay, and otherwise, what you do is if, so we'll have these two types, right? Like max agent and a min agent. So, so that way this state is a max state and this S2 and S3 are min states. So S1 is a max state and S2 and S3 are min states. Okay, so you try to put in that logic here. Now, if the state is a max state, you do something. There's some action you do. And if it's a min state, if state is min state, there is some other thing you do. Okay, so we have to fill this up. Okay, so I will just write other functions. Okay, some helper functions to fill in these two parts. Okay, so I will just call those helper functions as you call. Okay, so you return the max value of that state. Okay, so this is another function that you will write, or here it would be that you return the min value of that state. So these are helper functions, which again we'll write. Okay, so now let's just write the max value function. So what this is supposed to do is, this is what the max agent would do if he was at state, at this state. Okay, so what would the max value do? It would take each of its children, each of the possible actions, and those would be the min states, right? So at S1 is a max state, the children are min states. So then you get the value from the min states and choose the best, right? So you can do this like in an iterative manner. So initially the value is very small, say some minus infinity. It's a very low value. And as you see your successors, it gets better and better, right? So what you do is for each successor, so let's say for each successor, I'll just call this new state. So it's actually supposed to be action, which gives new state. Okay. So what you get, okay, right? So for each successive action, which gives you new state, then you try to find the min. That's going to be a min agent, right? A min agent is going to come in here. Right. So what you do is you call a min value starting from the new state. Okay. So here that's going to give you something like a -8. And then you have your v, which was minus infinity. So you just update it. So v is max of v and min value. Okay. So this is another function that you have to write. And you keep doing this. For each successor, you keep improving the value of v, and finally you just return v. Okay. Right? And the analogous thing you do for min value, right? So you have min value of states. So this is another helper function. So what you have now is you start off with a large value, v is plus infinity. So this is trying to mimic the min agent, what the min agent would do. So now what, it's going to be the same thing. So you have for each successor action. So this is, I'm just writing it very loosely, okay, but I hope you get the idea. For each successor action, which gives you new state. Okay. What you do is now v is min of v. And now what is going to happen at the new state? The next state is going to be a max agent, right? So here we had only 2 states, but what is going to happen is you have a max, then you have the min agent coming in, and again the next level is going to be a max player, and so on, right? So it goes on and on. So finally, here you have to call the max state, right? So the max value at the new state, right? And finally, you just return this v. Okay. So yeah, so how it would proceed is you start with the value here. The value in turn is going to call, this is a max state. So it's going to call, it's going to get into this function, the max value. And here it's going to call, the min value for this state. And that's in turn going to call the max, and so on till you hit the terminal. Okay. I hope this is clear to you. Are there any questions?
Ma'am, could you please show the code once?
Yeah.
In the max value and min value functions, won't it be better if we call like v is equal to max of v comma value of new state?
Yeah,
because
I think that
the
you
max
will hit the
value
terminal, right?
The terminal, yeah.
Yes, exactly. That's right. So you just call value of this, correct? So in the value, you're handling this, right? If the state is a max state or if it's a min state, correct? Yeah. So even here, you can just have it this way. Yeah. Yeah. Thanks, Advait, right? You said?
Yes, ma'am.
Yeah. So I hope this algorithm is clear to you all. It's proceeding exactly like your depth first search in some sense, right? You start off at the root and you go progressively to each of the successors till you hit the terminal, and then you come back. So at the last state, what happens? If it's a max player at the stage, at the level just before, it's going to call the terminal and it's going to have the value, and then it comes back, it finds the next guy, it tries to, that's the way it progresses, right? It comes, traverses this path and then this and so on, right? And it comes back and proceeds to the next. So that it's, in that sense, it's exactly like a DFS, but just that you have alternating controls for each state. Okay. Any questions on this algorithm? It's all good? Yes, no? You can type. It's clear? Okay. Okay. Cool. All right. So, yeah, so having said this algorithm, now what happens if, okay, so, if the other agent, I mean, this is a strategy that you devised, okay, and because you were very careful and you thought that the other guy is going to hurt you the most. Now, if the other guy, is not going to play optimally, so the optimal for him is to always choose the min, but if he's not going to do that, then what happens? Is it going to be bad for you, or is it better for you? I mean, what happens? This strategy, is it going to hurt you by playing this max min kind of a thing?
It's going to be good for us if he is not choosing the minimum value.
Yes, it's going to be better, right? Like, so who was speaking? Sorry, I don't know all the names. Umang. Okay. Yeah. So exactly what Umang said is right. So in this example, like the strategy you have decided that you will play is A2. Okay. Now the game is going to land up in S3. Now in S3, the best for this guy is to play B3. But if he plays B1 or B2, it's even better, right? So you expected -3, but then you're going to get even better. So this cannot hurt you in any way. It's the very safe strategy. Okay, and another point here is, I mean, there's some good things. These are some of the good things of this game. On the other end of the spectrum, what you have is this tree can become very large, right? Because you're expanding all possible actions for each guy, and all the the alternate moves and everything you're going to account for, and so the tree can grow very large. For example, in the case of Pac-Man, it's the game goes on and on, right? I mean, if each player is trying to help himself, or it can go for infinite amounts of time. So then this tree becomes very large, and you need all these terminal utilities to make any to decide on any strategy, right? So that can be cumbersome. So that's the case for most of these games that you see. Like, for example, even a game like tic-tac-toe, maybe you have this game, right, that one player marks a cross and the other marks, I mean, I don't know what symbols you use, but even this game, like, you start off with 9 possible moves, and in the next game the next player has 8 possible moves, and so on, right? So it's actually in the terminal you'll have about 9 factorial. Okay, maybe not all of them might not end up in like terminal. Maybe you will get a terminal state much before. It may not always be in the last. It's not always that you explore every possibility and then only you get. So what this number 9 factorial is when all these entries are filled up, right? So yeah, the game can end sooner than that if somebody wins, right? So even here the number is, the worst possible values is like quite large, and you have to account for that, and the tree can grow. And so this is just a very small game. Even here the number of terminal states can be very huge. Okay, so that's one issue with these min-max games, that it becomes very computationally expensive. So is there something better that you can do instead of explicitly taking the value of every state and trying to figure out, can you do something better? Okay, so that's going to be the next topic. So one thing that maybe I'll ask you only, what do you think can be done? So these when these trees, like, they grow very large, right? I mean, you have this huge kind of tree, and you have to wait for the terminals, right? Like, at this point only you get the utilities. So you have to actually simulate the whole all set of possibilities to know these terminal utilities and to backtrack up. So what is there something that you can do better? Any thoughts? Any ideas what could be done? Anything that you learned from your previous search methods? And there also you had these trees and you had DFS, you had BFS, and there also we tried to do some kind of optimization, right? We tried to speeden things up. Does anything strike you? Greedy? So Harshit is saying greedy. So can you just explain what exactly you mean? Use heuristics, Deep Desai. Okay. Yeah. So I'll come to each of this. So maybe Harshit, maybe you want to elaborate a bit more what you mean. Greedy method. So you mean like use some kind of heuristics? Are you to choose a local optimal? Here, actually, you're doing that, right? I mean, essentially you are doing this kind of a local optimal. Like what you have is something in the terminal states, and you're doing something which works best there. And at each point, you're trying to see in that local vicinity. Of course, it has to be propagated from the root. But if you had to do something even more local, how? What's the thought that you have? Yeah, I mean, this is kind of in track. So like this idea of, heuristics or doing something around in that vicinity, that is kind of the idea. So yeah, does anybody want to make any more attempts?
Memoization.
Memoization. So how would you do memoization here?
There may be some state which repeat, like once you made a trigger, the state is repeating.
Can you say that again?
And there may be some state which repeat after some, like one time you made a tree where S2 came in second level, then S2 come again in fourth level.
Okay, yeah. So in that case, the tree repeats, so you can, kind of compress the tree and use that. Right?
Yes.
That's what you're saying. Yeah,
Yes,
that is possible. I mean, if all the terminal utilities finally you get are the same, yeah, that is definitely one option. So you keep track of the search tree in the state. Like you're trying to do something similar to having a search graph, an equivalent search graph instead of a search tree. That is true, but at least like for one set of trees, you have to, compute, you have to go all the way till the root. I mean, sorry, all the way till the leaf, not the root. You'll start from the root and go all the way till the end, the leaves. Okay, so the issue is more about the depth being very large, right? Right, you get what I'm saying?
Yes, ma'am.
Yeah, so is there something you can do about the depth? So Rishabh is saying dynamic programming. So how do you propose dynamic programming? Use probability. Okay, so Kunjan, you want to explain a little more? Just an idea. Okay. So yeah, probability is, I don't know, like here your assumption is that the agent is bad. Okay, the agent is going to hurt you. You know that for a fact. So there's nothing random about this kind of a model that we are doing. All agents are trying their best to maximize their own utilities. Okay, so we will do like what Kunjan said, like that idea will come up. We will look at different kinds of agents. We'll look at random agents. And in that time, the notion of probabilities will be useful. But in this particular setup, when you're dealing with an adversary, probabilities, it's not immediate whether probabilities help here to improve the computations. I don't know, Rishabh said about dynamic programming. I don't know what the idea is. Don't Deep Desai said.
Ma'am,
Yes, Rishabh.
yes, ma'am. Actually, initially, Himanshu Singh told that the memorization, and because as you already told it, there will be some state which will repeat it, so we can use a dynamic programming for for learning those states. We can use that.
Okay, so that's what you meant. Yeah, definitely. If a tree is going to repeat further down, that is definitely you can you can store something. You can do. You don't have to repeat that computation. Definitely, that is something you can do. But here, I think the issue that we are talking of is that even for a subtree, even when things don't get repeated, and when you have to go all the way till the end of the tree. So here it's not the complexity is not because of things getting repeated. Like even in the tic-tac-toe game, if you see, right, it's not, the issue is not there are not going to be repetitions in this game tree. The issue is about the number of states itself being very huge, the terminal states itself being very large and without repetitions and with a huge depth. Okay, so so that's the issue. So Deep said something about don't explore subtrees, which are obviously bad. Yes, that is something we will do. There will be, like, when you do this analysis, there'll be some parts of the tree which are going to hurt you. So if you know that beforehand, don't even get into those subtrees. That idea is useful. And Sanjay, maybe start from and build upwards. Okay, yeah, that's what we're doing now. So I will come to Deep's idea a little later. But before that, I just want to talk of a little bit even simpler idea first. So that is of, cutting off the depth. Right? This is something you saw in DFS, where you don't go till the end. You just say that you're going to do some 4 levels. Okay, like this much only you're going to do. It's as if these are going to be your terminal states. You will assume like that. Okay, and then you will do the same min-max kind of thing. But now the issue is, how do you get the utilities here? The utilities are only for the terminal states. So how are you going to get utilities for these intermediate states? Right? So that brings us to this notion of what are called these evaluation functions. Okay. So in the sense, yes?
Ma'am, it is similar to the calculation of the gain or Gini index type thing.
Which one?
Ma'am, as in the decision tree algorithm, generally we will do the pruning, but we will get the pruning when we are calculating the gain on any node. So you are doing the same thing or something else?
So it is, okay, in some sense, something similar, but there is some design element which is going to come in here. Okay, like in the case of decision trees, maybe you do something like you consider some notion of entropy, right? The information held, right? So here there is no probability. Okay, so the thing is about, you need to measure like how good each of these intermediate states are. So in that sense, yes, it's the idea of goodness of a state, goodness of these intermediate nodes, but there's no probability or no such thing here. So you have to come up with some way to see if each of these states are good for you or not. Okay. Yeah. So what you can do is, come up with some function. So this is kind of like the heuristic idea, where you said that for each state somebody told you that this is this is how far you're from a goal. So that was in the case of single agent search. So it's a similar idea here, but rather than how far you're from the goal, you can have some explicit functions, like you can have some kind of features for each of these states. So let's say this function, you can have some combination of feature values. So maybe some f1, so w1 f1 plus some weighted combination of some features. Okay, so maybe some wn fn. So you decide beforehand that these are the features which are useful to you, and then you have some way to combine them. In what it should capture is that if there are some good things of this state, it should have a larger value. So it is some kind of a proxy for the utility, but just that it's for these intermediate states. For example, in maybe in Pac-Man, right? Because that's the example that you're seeing in your labs. So in Pac-Man, you have like different food states, right? Like you have this kind of a board, and you have Pac-Man, and there are these food states, and there is a ghost here. So I don't know, maybe I don't know how to draw a ghost, but okay. So Pac-Man is here and there's a ghost. And so one thing you want, what are the things you want in the terminal, right? You want, all the food to be clear. Okay, so maybe one possibility is number of food remaining, right? So if the number of food remaining is large, then it's a bad state. So it should be, you can have one feature which is, inversely proportional to the number of food remaining. Okay, maybe another possibility is to, tell me some other things. What are the things you want in the terminal? I mean, it's inspired from the terminal, right? I mean, you want to go towards the terminal, but before that, you want to see, whether it's good or not. So what are some other things you want?
Maybe distance from ghost.
Distance from ghost. So you want the distance from ghost to be less, more? More, right? So you can have one feature which is proportional to, distance from ghost. Okay.
And at the same point of time, nearest food distance.
Yeah. So you want another feature could be like, you want to be close to the food. Right?
Yes, inversely proportional to
inversely proportional. Yeah. Distance from food or nearest food, or that is up to you. Okay, so there are these kind of features that are very obvious to you from the game. So for each state you can design these values. I mean, you can create a function like this, and you can have some weights. So this is going to tell you how important is each. Now, you have these pellets, right? I mean, you have these big food particles. Okay, so maybe that is not too critical. So that is maybe less important. I don't know. Or, so there's these weights also give you some flexibility. So these are just some numbers. Okay, so these are again some functions, or these are like features. So F1, F2 up to Fn are some features, and W1, W2 up to Wn are some, numbers, and these are tunable. Okay, so what you can do is for each of these states, you can design this F value. Okay, and then use that. So consider as if your tree is only this much big, and these are the terminals. And at the terminals, now the utility is given by this this evaluation function, rather than the exact terminal utility, which is not available for these intermediate state. Use this evaluation function. Okay, so I hope this idea is clear. Any questions on this? Simple idea, right? Yeah, Rishabh, tell me.
Ma'am, in the slide you wrote that the function is inversely proportional to the number of the food remaining. I think it should be directly proportional. Why should be inversely proportional?
So if you have more food remaining, is it good for you or bad for you? What is your objective?
Ma'am, our objective to get the max to max food, na?
Yeah, you want the max food. You want all these food to be eaten up, right?
Yeah.
So at a state, you will have locations of these food items. Now, if there are only 2 food particles remaining, versus if there are 10 food particles are left on the board, right? Where have you made more progress? So number of food particles left on the board. So your objective is to finish all the food, right? So this is what is left. This is not what you have already eaten. Rishabh?
Yeah, ma'am.
Yeah, so which is better, is having 2 particles better or having 10 particles on the food? Where have you made more progress?
Yeah, when we have the less food.
Less food, right? So initially you started with some 50 food, there were 50 food particles, and finally you moved to 2. So that was more progress than 10.
Yeah, ma'am.
Right?
Thank you.
Right, yeah, so that's where you have this kind. So there is no hard and fast rule about how you want or how many features. This is entirely up to you how you design this, but it's just that, you know, if you have more features which are kind of correlated with your terminal utilities, then it's better. Your algorithm will do better. Okay, so you will work on this in your next lab assignment, but I just want to maybe show like one demo of, you know, these evaluation functions. That's something that I try to write. It's not a perfect thing, but just for illustrative purposes. Okay, so I will just use the Pacman. So I'll just show you 2 evaluation, a demo with 2 evaluation functions. So in the first evaluation function, I have these features F1, F2, Fn. I'm not going to use any weights. Okay, so let's just see how it performs. Okay, so this function is a different one. Let's try to copy that. Yeah. So it's just the same Pacman game with one ghost, and I've written it with an evaluation function, and I've cut it off at a depth 3. So the depth of the tree, I'm only taking up to 3 depth, and this is a ghost setting that's not critical. Okay, so I'm not doing anything. Okay, it's doing something. It's doing some good things. It's eating the food, but there are some issues, right, with this evaluation function. It got stuck at this part of the board. Okay, and again, it was getting stuck at a couple of places. It's doing what it has to, but it is kind of sluggish, maybe. Okay, so that's one thing. Like it's helping you. The evaluation function is no doubt helping you, but there are some of these issues. Now I will just show you maybe one more evaluation function, one more setting. See, again, it got stuck. Okay, so one more setting where I wrote a slightly better evaluation function. Okay, so it's the same evaluation function, but I've just used these additional weights. I've just tried to adjust the importance of each of the features that I used. Okay, so let's see how it behaves. Hopefully it behaves as I expect it to. These things are a bit random, right? Depending on the setting, yeah. Okay, so it's started off well. See, so it didn't get stuck at this point. So I kind of used the same seed so that, the starting point is the same for the ghosts also. So this is happening. It did do some dance here. But by and large, there was an improvement in the way, it was doing. So it again did some kind of dance again. Okay, so this is just to give you an idea of how evaluation functions help. Now if I didn't use this evaluation function, so you will also see in your labs, if you don't use the evaluation function, it can take more time for it to do, and a combination of all these things, the weights, the features, everything helps. And so that's something that you should also use when you design when you work on your labs. Okay, so yeah, okay. So I think, again, we're running out of time. I wanted to do one more idea, but okay, let's do that tomorrow. So I will stop here for now, and maybe I'll hang back if there are any questions. If not, yeah, thanks, everyone.